So as I promised you guys, I decided to make a video on Nyquist diagrams. So first of all, you're probably wondering, what is a Nyquist diagram? Well, a Nyquist diagram is a polar plot of your transfer function. Once I figured out that this is what a Nyquist diagram is, it made a lot more sense and I was able to actively take steps in learning it. So, what is a polar plot? Well, all a polar plot is, it's a graph of magnitude versus phase. So, how do we graph a Nyquist diagram? Well, for all intents and purposes, let's say the transfer function is h of s, okay? How do we graph magnitude versus phase on this? Well, either we're going to be given a table, or we need to come up with a table. We need to figure out the magnitude of different omega values, and figure out the phase of different omega values. So the way that we do this, step 1, plug in j omega for s. Then, plug in different values of omega. Generally, for your omega values, you want a longer range, a bunch of different values, to give you a feel for what's actually happening inside of the Nyquist diagram. So how do you find magnitude and phase? Well, after I plug in omega, you take the square root of each term squared, and that gives you your magnitude. And to get your phase, it's the arctangent of imaginary over real. So let's say I plugged in omega equals 1. Plug in omega, j omega, that's 1j. And you're probably wondering, well, how do I get the phase from this? Well, there's a hidden 0 here, because you can add 0 to anything, and it doesn't change the value of the number. If you do that, you end up getting the arctangent of 1 over 0. And you're probably like, well, I can't divide by 0, what does that do? Well, whenever you divide by 0, that just means that this approaches infinity. So what's the arctangent of infinity? Well, you can type it in your calculator, pick a really high value, and take the arctangent of it, and you'll get 90 degrees. But there's something more that I want you to see here. Pick any value, any positive value that you want of omega, any value. No matter what you plug in, you still have no real value. Like, your real is still 0. This is always going to be plus 0. So whatever you do, you're still going to have a division by 0 when you're getting the phase. Which means that for every real value of omega, you have a phase of 90 degrees. That's important because we're trying to analyze this transfer function and figure out the trends behind it. What if I plug in 0? Well, that means the whole thing is 0. What's the magnitude of 0 plus 0j? Square root of 0 squared is 0. And arctangent of 0 is just 0. Hopefully you guys understood all of that. If, let's say I wanted to plug in 10 here, that's 10j. If I want the magnitude of that, I take the square root of 10 squared and I get 10. And if I want to take the phase of that, it's the arctangent of 1 over 0, which is 90. Exactly like I said. And technically it would be 10 over 0. The actual value here, either way, you're dividing by 0. So it approaches infinity, which is going to be, and so when you take the arctangent, it actually approaches 90. So you start plotting these values. On the right here, on the left here, you have your general contour. This is what the standard contour for a Nyquist diagram is. It means that you can plug in points on this thing and see where they map to on the other side. It's just a different way of finding points for your polar plot. Now, when we graph the Nyquist diagram, we have points, so we know that it's at 0 because of the 0, 0 here. We know that it's 1, 10. No matter what we do, whatever positive value we plug in for omega, it's going to keep approaching 90. Maybe you can see that trend. Well, 90 degrees, it's always from the positive real axis. This is your starting point, your reference. So notice this is 90 degrees right here. This is a 90-degree angle. So this is the first part of your graph. You go up and you go up and you never stop going up. You actually continue until you get to infinity j. Now you're probably wondering why I also have the bottom of this graph shaded. Why do I have the bottom of this graph shaded? Well, it's because it's magnitude that we're graphing. If I have a magnitude of 6, and then I have a magnitude of -6, either way, the magnitude's still 6. The sign doesn't matter. That's actually why this mirror works. All Nyquist diagrams are going to mirror each other because of this simple reason. We're graphing magnitudes, and magnitudes, the sign and the direction don't really matter. So that means whatever's on the top is also on the bottom. Whatever's on the bottom is also on the top. But now there's another thing that we need to look at here. So this whole line, these two, actually maps to these parts of the Nyquist contour. And usually this contour is given to you, so that's not something you need to memorize. So now we need to figure out, well, where else does this go? We can actually look inside of this circle right here. If we could say that this, let's say this has a magnitude of epsilon, and we want to make epsilon approach 0. So we want to find how this is going to connect. Well, let's say that here, let's say that I plug in S equals, let's say I plug in omega equals, if I want to know what's in the left side of this graph, I need to figure out how to get my angle to equal -180, okay? Is there any way to do that with my current transfer function? The arctangent of, was it 0? Let's see here. What's the tangent of 180? I don't know. I can't remember. Tangent of -180. I'm typing this in my calculator. If we can figure out what values we can get for -180, we know whether this Nyquist plot is going to go left or go right. Okay, so the tangent of -180 is 0. So that means that if we want to get a phase of 0, if we want -180 degrees as our angle, that means we'd have to have the arctan of 0. Which would mean we'd have to have a real value. But we just said that there's no way to ever do that. So technically, this is the complete Nyquist plot. But you actually have to connect the plot. Notice that this whole thing never ends. You have to connect it. See, it makes a full loop. So you have to connect it, and you can figure out what direction that is. So in this case, it's going to be going to the left, like this. And you're probably wondering how do I know where to put the arrows? The arrows just represent omega is increasing. So if omega was 0, I was here, and I kept going up and up and up and up. And the arrow doesn't change. Once it starts, it has to continue. So now if I type this in Wolfram Alpha, you'll see that I got the correct Nyquist diagram. S. See that? Notice that they have a dashed line right there. That's because, technically speaking, everywhere on that dashed line, S has a magnitude of infinity. So there's no value you can actually plug in for omega to get that. And it's going to be mapped to the left half plane because when your contour is mapped to the right half plane. Hopefully that makes sense. If it doesn't make sense, ask me. So, now you're probably wondering, okay, that's all great. I have the Nyquist plot now. Well, is it stable? How do I know if it's stable? Well, here's where the fun part happens. Remember when you had a transfer function, let's say it was a fraction, let's say it was 1 over 1 plus 2. No, wait. Let's say, I'm going to set this down for a second, but you can still hear me. Let's say my C of S was 2S plus 1. And then I wanted to get the Nyquist diagram of this. Let's say this is the standard This is 2s plus 1. This is output, this is input. I'll call this C of S. And then you can label this whatever you want, A. Let's call it A, and let's call it B. So that means our transfer function is going to be 2s plus 1 over 1 plus 2s plus 1. Maybe I shouldn't have used a plus 1 here. Maybe this was not a good example, but I'm going to show you this with something else. Let's just erase the 1 for right now. I'll add that in later if you want. Okay, so let's assume that the C of S was equal to 2s, and then I had my transfer function as 2s divided by 1 plus 2s. So if I asked you to find the poles of this function, what does that mean? Well, the poles happen when I divide by 0, basically, no matter what. So how do I divide by 0 in this? The only way I could divide by 0 was if this 1 plus 2s was equal to 0, okay? So that would mean 1 plus 2s equals 0 for finding the poles. Why do we need to find the poles? Because we're trying to figure out if the system is stable or not. So now what? Subtract the 1. That means 2s would equal negative 1. Have you seen this value before? Where did that negative 1 come from? Well, we solved for the poles. If we have a pole at negative 1 in our new system, then that means we would have a marginally stable system. Hopefully that makes sense. If it doesn't, go back and rewatch the last minute of my explanation. Feel free to comment on this video and ask me for help. So that's where the negative 1 comes from. If you have no idea what I'm talking about, just keep watching and I'll explain it. So, when we graph this transfer function, or Nyquist diagram, and I'm just going to type it in because I already explained how you can find the Nyquist diagram, so I'm just going to look this up so I can show you how to figure out whether it's stable or not. Nyquist diagram of 2s over 1 plus 2s. In the meantime, while this thing is loading, I want you to realize something. If this part was equal to 0, let's say I only wanted to look at the denominator of this because I'm only looking at the poles. I only care about the poles, right? So if this whole thing is 0, you could say that it's a 0 of the Nyquist diagram. But this whole thing is also the pole of the other system. So this is actually a 0 and a pole. It's a little confusing, but try to stay with me here. You know that the original poles of your transfer function are going to be right here. You're looking for the poles. But if we isolate this for the Nyquist diagram, then it becomes a 0. If that doesn't make sense, just try to avoid the terminology. Anyway, so I looked up the Nyquist diagram of 2s over 1 plus 2s, and I get this super pretty circle with a, looks like a radius of 0.5. Yeah, it is. Cool. So I get this circle, and it loops around. Radius of 0.5, diameter of 1. My apologies for my bad drawings. This is a 1, and it goes this direction. Is this system stable or not? Well, this is the criterion that we need to know. Z equals n plus p. What does n mean? N is the number of clockwise encirclements around the point minus 1. Why minus 1? Well, remember when you're looking at stability just of this function, you were looking at, is it in the right half plane? And then if it was, then the system was unstable. And if it wasn't, then the system was stable. And if it was on this line right here, the axis, then it was marginally stable. This point is at 0, 0, okay? But when we map this into the Nyquist diagram, we're looking at the poles of the transfer function. And the transfer function was 2s over 1 plus 2s, and the poles of that was 1 plus 2s equals 0. And then we saw that that would mean that 2s would have to equal negative 1 in order for us to find a pole at that point. So that means that when we have a Nyquist diagram, we actually only care about the point -1, because that 0, 0 point was mapped to negative 1, 0 in the Nyquist diagram. Hopefully that makes sense. Let me know if it doesn't. Anyway, so does this graph have any clockwise encirclements around the point -1? Nope. None. So n equals 0. Does this diagram have any right half plane poles? Well, what's our pole here? 2s equals negative 1. That means s equals negative 1/2, which is right here. Is that in the right half plane? Nope. So what does this mean? Z equals n plus p. Z equals 0 plus 0. Z equals 0. And that means it's stable. If z was not equal to 0, if z is any value besides 0, that means it's unstable or marginally stable. If z was 1, z was 2, it would be unstable. Let me know if you understand all this, and that's the gist of it. Figuring out that the 0, 0 point maps into the -1 point is an important key in understanding what a Nyquist diagram is and the uses that it has. It's just a different way of finding stability. And then we can make small changes to this function, and this maps to very small changes in this diagram. Let's say I wanted to take my original function here and add 1 to it, okay? Now watch what happens. I have 2s right here, and I'm going to add 1 to the original function. My original function was 2s, so I'm going to add 1 to that on the top, and then add 1 to that on the bottom. Okay, ready? Would you look at that? It looks almost exactly the same. Is that the same graph? That's pretty darn cool. So notice that it didn't really make a difference. I don't think it made any difference at all. Did it? Let me see. Oh, wait, no, it just doubled the radius. Yeah. Because that's 0.6 and that's, yep. Wait. But the other one had a 0.5 value right here in the middle. This is a 0.75 value in the middle. So that means, yeah, the radius was cut in half then. Yeah, so the radius was cut in half when I made that small change. But my point is the general shape remained the same. So what if I had something like s plus s minus 1 divided by 1 plus s minus 1 for the transfer function of a different function here. Well, it looks kind of really strange actually, because this 1 value right here is going to be all of your, this whole segment is going to be all of your positive values of omega. And then it still has to connect to itself in the left half plane because the contour is in the right half plane, so it gets swapped when you plug it in. Is this stable or not? Try using the rules that I just explained to you to figure it out. Well, how many clockwise encirclements is there around -1? We have 1 clockwise encirclement. And how many poles are in the right half plane? Let's see here. We had s minus 1, which means we had 1 pole in the right half plane. So for n, we said we had 1 clockwise encirclement, and p we said we have one pole in the right half plane. Z equals n plus p. Z equals 1 plus 1, which is 2, which means the system is unstable. Hopefully all of this made sense to you, and let me know if you have any questions. Thanks for watching, guys.